Hi, everyone, and welcome to this next installment of algebra. In this video, we're going to continue with our basic introduction to functions. We haven't been talking about any one specific type of function yet, more just functions in general. So this video will be a continuation of the last one. In our previous video, we talked about the definition of a function, how to identify a function, domain and range of a function, evaluating functions, what it means to graph a function, and a couple of basic approaches to graphing functions, plotting points, and using the graphing calculator. So this next video is titled More on Functions. Oop. There we go. Just more on functions. We're going to continue talking about functions. So in this video, I have four items on the checklist. Testing equations for symmetry. So symmetry is topic number one. We have a couple of slides on that. Even and odd functions, a couple of slides on that. Then we're going to talk about intervals of increasing and decreasing and relative maximum minimum values. And then we'll talk about piecewise defined functions. So first thing, what does it mean for an equation to possess symmetry? What is a symmetric equation? So here's three examples of graphs. Each one of these is a graph of an equation. We don't need to know what the equation is, right? But each one of these graphs corresponds to an equation, and each of these equations has symmetry. So if we look at the first one, over here on the left. So ignore the other two, right? Just look at the one on the left. This is not two separate graphs. There's not a pink graph and a blue graph. This is one continuous graph, right? So on this graph, just the positive y values, the top half of the graph is colored pink and the bottom half is colored blue, but again, it's one graph. If we were to flip this graph, reflect it over the x-axis. So if we were to just take the entire graph and rotate it that way. So the blue part moves to the top and the pink part moves to the bottom. We're going to rotate around the x-axis this way. Well, the picture doesn't change. I mean, what will change in this one, because it's colored in, but if this graph was just all in let's say black, you wouldn't be able to tell the difference. The blue part becomes the pink part and the pink part becomes the blue part. So there are no new points. Every point that was on the graph before you flip it is also on the graph after you flip it. And there's no new points, no points left behind. Right? And this happens when every point, and I'll just highlight this. Oop, that's not a highlighter. Every point. Well, first of all, every point could be described as an XY pair. So every point XY that is on the graph, also there is another point, which is X comma negative Y. That means 2 points. That means 2 points have the exact same X value. So let's say, for example, let's look at maybe a specific example. Let's say the point 4, 3. Maybe that's the top one in yellow. Well, for every point xy, there's also another point out there, which is x negative y. So that means the exact same x value, and the y value is the same number, different sign. So if the first point is 4, 3, the second point is 4, negative 3. And this has to be true for every point on the graph. There are two copies. There are 2 copies of every point. One with a positive y and one with a negative y. Same x value, one with positive y, one with negative y. So if this is true, we say that the graph is symmetric with respect to the x-axis. Okay, and then the next two definitions work in a very similar way, except when we're talking about y-axis symmetry, right? So I'm talking about the middle graph here, right? Y-axis symmetry means if you were to reflect the graph side to side, so the left side becomes the right and the right side becomes the left, it wouldn't change the picture, and it wouldn't change the graph. And this happens when for every point on the graph, every single point, oh, I did it again, yellow pen. I need yellow highlighter. For every point on the graph, x, y, there is another point, which is almost an exact copy, except one has a positive x and one has a negative x. So if this point over here on the right, let's say that's 5, 2, then this point over here on the left would be negative 5, 2. Right? 2 points, 2 copies of the same point, except that the x value has different sign, one positive, one negative x value. And when that's true, we say the graph has symmetry with respect to the y-axis. Or if you flip the graph over the y-axis, you don't get a different picture. Most graphs don't have symmetry. So, like, for example, let's say we have, let me use blue for the first one. Let's say we have this graph right here, right? If we were to flip this over the y-axis, so the left side goes to the right and the right side goes to the left, what would happen is, well, this part of the graph right here would go to that side, right? And this part of the graph would go to the other side. So we would get a completely new graph, a completely new set of points, right? All except for that one point on the y-axis. Every other point from the blue graph is not on the red graph, right? So this is an example of a graph with no symmetry. This came from an equation with no symmetry, right? The vast majority of graphs out there, the vast majority of equations do not have symmetry. These are 3 very specific cases. Keep that in mind. This is not the normal. This is special case number 1, x-axis symmetry, special case number 2, y-axis symmetry, and then finally special case number 3, symmetry to the origin. But these are indeed very special cases, very specific cases. The third graph on the right, symmetry with respect to the origin, that means it's just combine the first two. Combine the first two. The first one we flipped vertically. Top went to the bottom, bottom went to the top. The second one, left goes to the right side goes to the left side. You get the same picture. The third graph, the one on the right, symmetry with respect to the origin, if both of these reflections happen. So let's say, let me go back to blue, 1. Reflect over the x-axis, and then 2, then reflect over y-axis. So we're doing both. It's a 2-step reflection. So if this is one graph, remember, this is one graph. But let's just look at the blue part. Just focus on the blue part of the graph. If I was to reflect that or flip it over the x-axis, right? So I'm flipping it over the x-axis. Then this part of the line would go up that way, right? And this part of the graph would go there, right? That wasn't there originally. That was not there originally. So that is just reflecting over the x-axis. But then if we take that new piece of graph right here, and then step 2, take that and flip it over the y-axis, well, then this goes over here, and you actually end up with that, right? So if this part of the graph reflects vertically first, up, down, and then reflects horizontally, left, right, it ends up on top of the pink part, right? And the pink part, if you do the same thing, I don't think I have pink as a color, but I'll just use, maybe I'll use orange. Okay, so if we take this original pink part of the graph, we flip it over the x-axis, it'll end up down here. And then, so first we flip it this way, and then we flip it this way. Then this orange piece goes over here, and we end up with, let me get rid of all this extra stuff. Right, we end up with the same graph, right? If the equation is symmetric to the origin is the point 0, 0. Remember, the origin is the point 0, 0. Then if you reflect the graph vertically, top to bottom, and horizontally, left to right, both of them in 2 steps, if you get the exact original graph back, then the graph is symmetric to the origin. And that's true. So let's start writing down here at the bottom what has to be true. All right, so for symmetry to the x-axis, or in short, x-axis symmetry, the point xy and x comma negative y both have to be on the graph. You have to start with both points on the graph. For symmetry to the y-axis, for every point x and y, every point on the graph x and y, you must also have the point negative x and y. So x and negative x have the same y value. For the first one, it says y and negative y have the same x value. The third one, if for every point on the graph x and y, you must also have the point negative x and negative y. And so that's our test for symmetry if we have the graph in front of us. If we have the graph, but we're not really, when we say symmetry, we're really referring to the equation that the graph came from. So we don't always have the graph to just sort of look at and say, okay, what would happen if I flip this graph left to right? Or what would happen if I flip this graph top to bottom? So if we take the graphs away and just what the last thing I wrote on the bottom of the screen is over here. Right, this is, let me go back one screen. So this part, and this part. Right, that is on the next slide. X-axis symmetry for every point xy, the point x negative y is also on the graph, and so on. So it's the same 3 statements. Now, how do we use this? Well, here's an example. Without graphing, determine whether the equation has a graph that is symmetric with respect to the x-axis, the y-axis, or the origin. This is a 3-step problem, right? Step 1, test for x symmetry. Step 2, then you got to test for y symmetry. And then step 3, you got to test for origin symmetry. Now, most equations don't have symmetry, right? I said that earlier. Some do, special cases. And occasionally, you may get an equation that has more than one. It has x-axis and y-axis symmetry, or x-axis, y-axis, and origin symmetry. Those are very unique cases, but it's possible for an equation to have none of these, to have one of these, to have two of these, and to have all three of these. So we got to always test all three. This is how we solve an equation, a problem like this. Test for symmetry when we're given an equation. Now, we're going to use the previous slide. When we're testing for x-axis symmetry, what we do is we replace the x and the y with x and negative y. So we take the equation. We take the equation and we take this and make it that. Or basically, we replace y with negative y. We replace y with negative y and then see what happens. So let's write it like this. So y becomes negative y. That's what we have to do. So we do this, and then we see what happens. The test for y-axis symmetry is the reverse. We replace the x with a negative x, and then see what happens. And then the test for origin symmetry, we take the x and replace it with negative x, and we also take the y and replace it with negative y, and then see what happens. When I say see what happens to the equation. Do we get a brand new equation? Or do we get the exact same equation back? So if any of these three, what I have in red, these three boxes, if any of these, if I do each of these and I get the original equation back, if any of these gives me the original equation, then we have that kind of symmetry. So let's look at the first one. I'm going to rewrite the problem, except instead of a y, I'm going to put a negative y. So negative y equals x squared plus 10. Negative y equals x squared plus 10. Now, solve for y. Get y by itself. Well, we can take both sides of this equation and multiply by negative 1. Because that'll get rid of the minus sign in front of the y. And that gives us y equals negative x squared minus 10. Is that the original function? Or is that the original equation? No. This and this are not identical. They're not exactly the same. So, answer is nope. Doesn't have it. Doesn't have x-axis symmetry because we don't get the original equation back. Okay, let's try it for replacing x with negative x. So instead of y equals x squared plus 10, I'm going to write y equals negative x squared plus 10. Right, so instead of x times x, it's negative x times negative x, and negative x times negative x, the negatives cancel. Negative times negative is a positive, so we get y equals x squared plus 10. I'm going to circle the first one in red because that was a no. I'm going to circle the second one in green because that is a yes. This equation has x-axis symmetry. It may also have origin symmetry. Don't know yet. So to test for the origin, we do both of these things. We combine the two. instead of y equals x squared plus 10, we do negative y equals negative x squared plus 10, right? We swap out the x with a negative x, we swap out the y with a negative y, and the negative on the x cancels off because of the square, but we still get negative y equals x squared plus 10. And that's exactly where we were on step 1, negative y equals x squared plus 10, which gave us y equals negative x squared minus 10. Going to circle that in red because the answer there is nope. No, it does not. Nope, nope, but yes for x-axis symmetry. So this is the approach. You replace x with negative x, see what happens. Replace y with negative y, see what happens. And then do it for both variables at the same time. And by see what happens, I mean, do you get the original equation back? Or do you get something different? Okay, so that is it. That's symmetry of equations. We're talking about equations here, not functions. Equations, because some equations are functions, some equations are not functions. They're relations, but not functions. Okay, so now next on our list, even and odd functions. Even and odd functions. So when we're talking about equations, we're talking about symmetry. When we're talking about functions, we're talking about even versus odd. Now, right here, I have two graphs that look identical. They're both the graph of x squared. On the left, we're using the notation for an equation, the equation y equals x squared. And on the right, the function f of x equals x squared. You know, it's two ways of talking about the same thing, just in two different contexts, right? I could measure something in pounds, or I can measure it in kilograms, or I could count out some, I could count out $10 using dollar bills. I could count out $10 using quarters, right? It's different ways of describing the same thing. Every point on the graph of an equation, right? I'm on the left here. Every point on the graph of an equation, we use x and y. We use x, comma, y. When we're talking about functions, well, let me write this in the middle. Y is equal to f of x. Right? This is the connection between equations and functions. Y and f of x are the same thing. It's just two different languages. Right? One is the language of equations. The other is the language of functions. It's all the language of algebra or mathematics. So we may say these are like two different dialects, maybe. So we talked about this. We just finished talking about what it means for an equation to have y-axis symmetry. We just talked about that. That means if the point x and y is on the graph, then the point negative x and y has to also be on the graph, right? The plus x and the minus x both give you the same y value. So if our function has y-axis symmetry, we just don't use the word symmetry with functions. It's a different sort of, it's a different language, a different subset of the language of algebra. When we're talking about functions, we call it an even function. Right? So even function, y-axis symmetry, it means the same thing. When we're talking about symmetry, we say the same y value as both plus x and minus x as the corresponding x value. Or x and negative x have the same y value, maybe is a better way of saying that. With functions, f of x is equal to f of negative x. So f of x is a y value and f of negative x is a y value, and the equal sign is saying they're the same y value. So it's, yeah, again, it's just the same definition. We're just looking at it in a slightly different way. So that's even functions. Even function is the same as y-axis symmetry, just in a different language, right? In the language of functions. Then we also previously talked about origin symmetry. Now, an equation, right? Again, these two green graphs here, it's the same graph. One is coming from the equation y equals x cubed. One is coming from the function f of x equals x cubed. But again, as always, y is equal to f of x, and that's our connection between equations and functions. So if the graph has symmetry with respect to the origin, or if the point x and y is on the graph, then the point negative x, negative y is on the graph. Just sort of translating that from the language of equations to the language of functions, we get f of negative x is equal to negative f of x. All right, so even functions, f of negative x equals the original function f of x. Odd functions, f of negative x equals negative f of x. Okay, I'm going to go back one slide. So even function, they're the same. I'm looking down here on both slides. So right here and right here, it's almost the same, right? It's almost the same. The only difference is on the even definition of even functions, there's no negative sign on the right. It's f of negative x equals the original function f of x. On the next slide for odd functions, f of negative x is equal to negative f of x. Again, these are very special cases. The vast majority of functions are neither. They're not even and they're not odd. So we've talked about origin symmetry for odd functions. We talked about y-axis symmetry for even functions. But we don't talk, let me go back a couple of slides. We don't talk about the one on the left when we're talking about functions, right? This one over here doesn't apply. So for functions, this one's even. For functions, this one's odd. And the one on the left is not a function. Is not a function because one x value cannot have two y values if it's a function. Okay, so that's not a function. So that's why with equations, there's three. There's x-axis, y-axis, and origin symmetry. But with functions, there's only two, only even and odd. So let's look at a problem. So this is how we're going to do our test. Test if a function is even or odd. This we could do in one step. We don't have to test them separately. So basically what this definition is saying is step one. Replace the x with a negative x and then see what happens. See what happens. Right? This is step one. Replace x with negative x. So if you do this and you get the original function back, if you replace x with negative x and that doesn't change anything, the function is even. if you replace x with negative x and you get the exact negative of the original function, meaning every sign changes, we say it's odd. And if neither one of those things happen, then it's neither even nor odd. Okay, so if you look at this one, determine whether the function is even, odd, or neither. Well, this one, it's a pretty quick one, because what we're doing is we're starting with h of negative x. So take the original function and replace each x with a negative x. The first negative x is raised to the power of 6. The second one is raised to the power of 10. So all we've done is we've replaced that x with that negative x. We've replaced this x with this negative x. Oop. The rest of the function stays the same. 6th power, 10th power, minus sign in the middle. So that's step one. Plug in a negative x. And then see what happens. Well, what's negative x to the 6th power? Well, it's negative x times itself 6 times. So what do you get when you multiply 6 negative numbers? Well, you get a positive number. Negative times negative is positive, times negative again is negative, times again negative again is positive, times negative again is negative, so on. So if you have an even power, an even number of negative signs, the negative is going to cancel off. So negative x to the 10th power is x to the 10th. And that is the original function h of x. So we plug in negative x, we get the original function back. This is an even function, which means the graph is symmetric to the y-axis. Even function, y-axis symmetry. Right, the idea of symmetry and even and odd functions are not two separate topics. They're very much related. All right, so that's symmetry and that's even and odd. So let's move on. The next problem is just going to take some review and then a couple of new pieces. So here's a graph, and I'll try to go through this one relatively quickly because some of it is, again, review that was covered in the last video. So the first A, B, C, and D, this will be review. So the domain of f, we have the graph of f over here on the left. Sorry, on the right. They're like, it looks like part of a parabola maybe. So the domain of the function is all the x values that correspond to this function. Now that arrow at the end down here, that means the function is continuing on forever. That means it's going down and to the left to infinity. So the x values keep going to the left and the y values keep going down. So the domain is the green part of that graph. The range are the y values associated with this function. And it looks like all the y values from 4 down. Let's color code over here. It looks like the range, all those values on the y-axis appear as points on the y values appear in points on the graph, So we could write the domain. We always start on the lower end, where we go left to right or bottom to top. Oop, there we go. So the domain of the function will be all the numbers from negative infinity up to, and let's see, if we're looking right here, that looks like it's not 5. 5 is right here, so 5.5. Negative infinity up to 5.5. 5.5 gets a bracket, so 5 would be there. Looks like right halfway between the 5 and the 6, so 5.5. It's a closed circle, so that means that endpoint is included. So we use a square bracket. This is the highest point on the graph. So we'll come back to this point. So I'm going to label that as the point 2, 4. Horizontal 2, vertical 4, so that's the point 2, 4. So domain, or the range, we're talking about y value. So the highest y value is 4. So the range of this function, we're going negative infinity up to 4. Infinity always gets a curved parenthesis. Now the zeros of the function, the zeros, this is the places where the graph, these are the values on the x-axis where the graph crosses the x-axis. It's sort of, it's almost like an x-intercept. It's going to be the same number as an x-intercept, but the x-intercept is an actual point. So if I'm looking right here, let me use red. This endpoint right there, that's a point on the x-axis. That's the point 5.5, 0. That's the point 5.5, 0. So the zeros of f of x, this word zeros, the zeros of f of x are the x values of the points on the x-axis. And there's another one over here. That looks like, well, this is -1. It's halfway between -1 and -2. So that looks like we've got the point -1.5 on the x-axis and 0 on the y-axis. Okay, so the zeros, we would say x equal 5.5 and x equal -1.5. We call them zeros because if you plug them in for x into your function, the function gives you a 0. It gives you back the number 0. So if the input is either one of these two numbers, the output is 0. Okay, let me move that point, a little arrow. Let's say this again is the point -1.5, 0. Okay. The next one, the point, or the value, what is f of -1? Well, what this is saying is, what is the question mark? -1 for x, question mark for y. That's f of -1. When the x value is -1, right? -1 is over here, right? When you're at -1 on the x-axis, what is the y value? Oh, it looks like there's a point right there. And that's the point -1, comma, +1. -1, comma, +1. So when the x value is -1, the y value is +1. So that is equal to 1. 1 would be the answer. Okay, so pause here for a moment. I'm going to erase almost everything that's on the screen right now. I'm going to erase almost everything on the screen. The only thing I'm going to keep is one of these points, the one that's relevant to the next couple of problems. Okay, back to the original graph. Now, E and F, the intervals where the function f of x is increasing, and the intervals where the function is decreasing. So for these two parts of the question, it's important. As you move left to right, so like if you put your finger somewhere on the graph and you move it, you trace the graph with your fingertip, you're moving in this direction. So this you would move like this way. Right? In this direction. Left to right. Like, it doesn't matter. There's an arrow on the left. That doesn't matter. You're not moving in the left direction. Left to right. As you move left to right, is the graph going up or is the graph going down? So as you move left to right, I'll start with F. I'll start with F because the entire part of the graph that's decreasing is on this picture. We don't need the arrow. So look at this. This section I just highlighted on the x-axis from 2 to 6. So from 2 to 6. For that portion of the graph, we could say the graph is decreasing because as you move left to right, the graph is going down, 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 down. Right, as you move left to right on the x-axis, this piece of the graph is going down. So the intervals on where f of x is decreasing, where we're talking about intervals on the x-axis, right? So from 2 up to 5, because this point right here, that ends at, oh no, that looks like, sorry, 5.5. 5.5. Okay, so this, where is 5? 5 is right here. So that is between the 5 and the 6. So that yellow portion of the x-axis is where the function is decreasing. Now let's look at where the function's increasing. I'm going to switch to a different color. So as we move left to right, if we were to follow the graph anywhere in this area, this region of the x-axis, as you move left to right, as you move as you follow the x-axis, I'll get this pen right eventually. Here we go. As you move this way on the x-axis, the graph is going up, 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 up. And then it turns around, so it's going down. Right? But for that green portion of the x-axis, the graph, the y values are increasing. When we're talking about when is the function increasing, we're talking about the y values increasing. Okay, so that would be the interval from negative infinity up to 2. I'm using open soft parentheses because we're not including 2. because the function can't be increasing and decreasing at the same point. So the endpoints we don't include. All right, so that's it. Now pause again. I'm gonna erase everything. So I'm gonna do some different shading. There's a lot in this video. This is a long one. The values for which f of x is less than 0. The values for which f of x is less than 0. So what does that mean? F of x is less than 0. So we'll say f of x is less than or equal to 0 means y values are 0 or y values are 0 or negative, right? Less than 0 means negative. So f of x is less than 0 means negative y values, and the or equal to means equal 0. So I'm going to highlight again. One day I'll get this right on the first try. So highlighter. Let's do a different color here. Let's go to orange. So this one here, we're done with this highlighting. Done with this highlighting. We're looking for the portion of the x-axis where the y values are negative. The portion of the x-axis where the y values are below the x-axis. So it looks like right here is where it starts. This is -1. So it looks like to the left of -1.5, all the y values are negative. We would say negative infinity up to and including -1.5. Up to and including -1.5. So now part H. Probably should have done H first and then G, but it doesn't really matter. To answer the question, any relative maxima or minima. Maxima is the word plural for maximum. We don't say maximums. We say maxima. We don't say minimums. We say minima. Minima. Okay. So this refers back to increasing and decreasing. So when the graph is increasing and then it turns around and starts decreasing, you get what's called a maximum value. It's just a high point in the graph. It doesn't have to be, for example, the overall highest point, but it's the highest point. We say this word relative max and min. That just means it's the highest point relative to the points close by, right? The points to the left go down. The points to the right go down. Relative to the points nearby, we get a maximum value. These are y values. Right? The maximum value or the minimum value is a y value. So the maximum would be 4. Because that point right there in red is the point 2, 4. 4 is the y value, so 4 is the maximum. Part I, and this one, we basically just did it. Part I, the values for which f of x equals 4, well, saying when the y value is 4, what is x? So that would be the other part of the point. Right, so the maximum value is the y value. The location of the maximum is the x value. And now the last part is f of 4 positive or negative. Well, this 4 is a different 4 than the 4 we just talked about. So in part H down here, the 4 that you see there is an x value. It's not this 4. Let's get rid of this. F of 4, well, that means we have to go over to 4 on the x-axis and then up to the graph and then over to the y-axis. So this y value is f of 4, right? We're looking at this point. The point when x is equal to 4, the y value is called f of 4. F of 4. That's above the x-axis. So that is positive. That is positive. All right, so this was 10 problems in one. So this was a long one. So let's move on. Got two problems. This one is actually pretty quick. So continuing on with our discussion on functions, sometimes we need to utilize what are called piecewise functions. With a piecewise function, it's exactly that. It's a function made up of 2 or more different pieces. And then when you have a graph of a piecewise function, you're going to have a graph made up of 2 or more pieces. So we have two pieces here. We have the part that is the function, and then we have the part that is the domain. The part that is the function and the part that is the domain. So if you were to graph, ignore the one on the bottom. If you were just to graph g of x equals x plus 3. We would get a graph that looks, and we'll talk about why this is what it is later. There's 4, 3, 2, 1. You would get something that looks like that. That's the graph of x plus 3. And then if you ignore the top and just look at the graph negative of x plus 3, you would get, use a different color. This is the graph of negative x plus 3. So what this is saying is, this would actually right here, this would be negative 3 on the x-axis. So what this piecewise function is saying, okay, look at the black graph first. This is the black graph. The x was 3. Don't use the whole thing. Just use the black graph for x values that are greater than or equal to negative 3. So we what we basically do is erase part of the graph. Right? We erase the part where for the x value is less than or equal to negative 3. And then if we look at the other portion, we look at this piece down here. Right? We're saying, okay, use that graph, but only part of it, only the part for x values to the left of negative 3. Only x values less than negative 3, so we're going to erase this portion of the graph. And so what we end up with is, this part came from the black graph from the first one, and this part came from the second one, the blue one. Right, so we get a part of the first function, part of the first graph, a part of the second graph. This is why we call them piecewise defined functions. So when we're evaluating functions, so I'm going to erase what's on the screen now. When we're evaluating functions, evaluate means plugging in. This is a topic from earlier in this chapter. Evaluate means replace or plug in. So g of 0 means put a 0 in for x. Well, where? Where does the 0 go? Does it go into that x? or does it go into that x? It can't be both. You can only plug it in for one of them. Does it go to the top piece or the bottom piece? Well, you got to see, where is 0? Where is 0? So for this problem, 0 is in there. 0 is part of the set of x values bigger than or equal to -3 because 0 is bigger than or equal to -3. So we use this part. So that is equal to 0 plus 3. We replace the x with a 0, which is equal to 3. Just got to make sure you're plugging it into the right piece. Oh, I can't stop doing that. Highlighter, there we go. So for the next one, g of -7, well, -7 is less than -3. So we're using this piece down here. We're using that piece, the second piece of the piecewise function. So for g of -7, that is equal to negative parentheses -7 plus 3, which is negative parentheses -4. It's -7 plus 3. Negative of a negative is a positive, so we get 4. Done with that one. Now if we look at g of -3, well, where does -3 live? Is it in the top piece or the bottom piece? Well, only one of them says or equal to -3. So that's actually going to be back to the top one. Back to the top one. So when we evaluate g of -3, we plug -3 into the top piece. So that's -3. Instead of x plus 3, it's -3 plus 3, which is equal to 0. So evaluating a piecewise function, you just got to make sure you're plugging the number into the correct piece. You're never going to use more than one. You're never going to use more than one piece of a piecewise function. Okay. And this is similar to what I just did on the previous slide. So I'm going to go through this pretty quickly. All right, so I'll use, let's say, just look at the first piece, f of x equals 2x. Ignore the x is greater than or equal to 0 part. If we graph f of x equals 2x, we get something that looks like this. And I'll talk more about this and actually in my very next video. But for right now, we could graph this by plugging in points or by typing this into a graphing calculator. Right? And then we'll look at this part in orange. 7. Well, what does the graph of 7 look like? That's saying every y value is 7. So ignore the 2x part. Just f of x equals 7. We go to 7 on the y-axis. So 2 units above 5. And we get a horizontal line. Every point that has a y value of 7. Right? So those are the two pieces. This is f of x equals 7. This is f of x equals 2. But redraw this graph. should, not exactly right, but this should be a straight line. And then this guy, yeah, again, let me make it so I could erase half at a time. Do that. And then that. Okay, so this is saying for the green one, for the 2x, only use the portion of that graph that's to the left of 0. Right? For x values less than or equal to 0. So the green portion has an or equal to, so it gets closed circle right there. And for the orange part, 7 if x is greater than 0, so we're only using the portion of the graph that has positive x values. That gets an open circle. So I'll move this label down here. This is f of x equals 2. The orange part gets an open circle because there's no or equal to. So we have a piece of the graph f of x equals 7. We have a piece of the graph f of x equals 2x. And this is a piecewise defined function. Okay, that is it for this video. If you sat through till the end, good for you. I mean, there's a lot of really useful stuff in this video that, we're, at least in this class, we're going to be using and referring back to. So it's just more tools into our toolbox. All right, that's it for now. I hope this was helpful.